Hello everybody, welcome to the ME 296 lecture on thermistors. We're going to cover what the thermistor is and then a couple of usage examples. So what is a thermistor? A thermistor is a type of resistor that changes value based on the temperature even more so than regular resistors do. Now this is not really a linear straight line process, but if we zoom in enough and over small ranges of temperature, we can treat our curve like a straight line, and we linearize this line as the equation shown in the middle of the screen. We have the change in resistance, delta R, equals the temperature coefficient K times the change in temperature. From this, there are two kinds of thermistors, PTC and NTC. PTC is positive temperature coefficient, where the resistance goes up with the change in temperature that increases, or a positive value of K. NTC is negative temperature coefficient, and the resistance goes down with an increase in temperature, or a negative K value. And with that, we're just going to jump straight into how they're used. The first use case is a current limiter. Ohm's law tells us that for a given voltage, the current is proportional to resistance. And we can use this to regulate current in systems that are getting too hot when there's a thermistor involved. Our example system has some input voltage flowing into a thermistor, where the symbol is a rectangle with those checkmark looking set of lines through it. And then that current goes through the thermistor and into the rest of the system. For this usage example, we're just going to ignore what the rest of the system exactly looks like and just know that it's going to be very sensitive to heat and should not get too hot, or maybe some plastic melts or something like that. So we don't normally have temperature as part of our circuit analysis, so we're going to use power as a proxy for temperature, because we can treat power and temperature fairly equally, because power leaving a resistor does so in the form of heat or temperature, so we're good to go there. So our power equation is power is equal to current times voltage, and since we're not affecting the voltage in this case, we have a set voltage generator. The only thing we can affect is current. And since we want the current to go down when the system gets too hot, we want a PTC thermistor. When it gets hotter, PTC means the resistance of the thermistor goes up, and Ohm's law tells us that a higher resistance for a given voltage is a lower current. So lower current, lower power. So let's see what happens when we turn our system on. First, system turns on. The temperature is initially low. The low temperature means low resistance in the thermistor. And so we have a high current from Ohm's law, and therefore a high power output, and that high power output heats the system up. As the system heats up, resistance begins to increase. Higher resistance causes current to decrease and then lowers the power output. This is not enough decrease in power, so the system continues to heat. So we have a higher resistance and a lower current and then lower power output. Now our current is low enough that the power output is such that the system begins to cool, the temperature goes down, and the resistance goes back to the medium level, and the current returns to its medium level. Now, if you were paying attention to the control systems lecture, you might see that this is a form of a negative feedback control system, and we're going to reach a steady state value or a set point value somewhere between medium and high heat on this. Now, if we wanted the system to get hot, like if we're starting a car in freezing temperatures, we would want an NTC thermistor, because that would increase our temperature rapidly instead of decrease it. So that's our first usage case. A second usage case is going to be reading the temperature digitally. This one's a little bit more complicated. We're going to need a voltage divider hooked up to a known voltage. And we need the voltage divider because we're going to need to be able to tell the resistance of our thermistor at any given point in time. And we don't We can't do it directly because reading the resistance requires whatever it is we're reading to be independent of everything else in the circuit, which is not helpful in this situation. So what we can do instead is use a voltage divider to take the voltage across our regular resistor that we're in series with, and then manipulate our math equations so that we can get our resistance of our thermistor at any given point based on the voltage, which we can just read in parallel. So it's very simple to do. So we're going to use our well-known voltage divider equation, and then we're going to solve for the current resistance of our thermistor, where X is the value of the resistance on our thermistor at any given point in time, R is the value of our paired resistor that is known, and VI is our input voltage. So we wind up with the resistance of our thermistor is equal to our known resistor value times the quantity of the ratios of our voltage input over output minus 1. Since we're looking for temperature, we need to get from resistance back to temperature. And if this was a 100 level class, we would just use that delta R equals K delta T equation. But we're looking for practical systems knowledge here, so we're going to use the Steinhardt and Hart equation. And Steinhardt and Hart went through a lot of trouble to derive an equation that does this for us in a fairly accurate way. There are 3 coefficients in the equation which are unique to each thermistor type or model. And most of the time these are provided with the thermistor when you purchase it, but sometimes we're going to need to determine these on our own. And this is not too much trouble, as we can set up a system of equations with 3 measurements at known temperatures, and then you just solve that system of equations. You have 3 measurements, 3 unknowns, you can solve that. And I'm not going to do that here as it's going to be a homework problem. I'm just providing context and a little hint about how to solve it. We're also going to be building this circuit for a lab coming up, so be familiar with the background, and it's going to help with the report. I'm also going to be providing the coefficient values for the lab, so I'm not going to make you measure the resistance and all that stuff at different temperatures and everything like that. So don't get too into the background of the Steinhardt-Hart equation. Just know where it comes from, that it's important to convert temperature from resistance of our thermistor. All right, well, that's all for now. Bye.